Welcome back to NE 630, nuclear reactor physics. Last lecture, I think you have the two visitors from the nuclear power station, and I hope that the presentation were of importance to all of you. I think it gives some feedback about the fuel management in the nuclear cores and also Fukushima nuclear accident. So today we will conclude chapter 2. And I hope next time we'll start chapter 3 about the neutron diffusion in nuclear reactors. So today we'll just give a brief introduction about the neutron kinetics in a nuclear reactor. So last time when I talked to you about the 4-factor formula and 6-factor formula, somebody asked about the effect of using natural uranium with graphite and whether you will be able to sustain a nuclear reactor just based on graphite or not. So this example here, I promise you to talk about the effect of fuel lumping. So if you do just graphite plus uranium, and you do the calculation, you'll notice that the thermal utilization is around 0.9, the fast fission factor is around 1.5, the resonance escape probability, if you just spread the uranium homogeneously in a graphite cell, the resonance escape probability is around 0.7 and eta is around 1.33. So if you calculate the infinite multiplication factor, you will notice that it is less than 1, 88% less than 1. So you will not be able to sustain a graphite moderated natural uranium reactor. So the solution is if you will do what we say fuel lumping. So you will have the fuel in lump. So this is the fuel here, fuel, let's say fuel rod or whatever, and the moderator is here, and this is the fuel. So what happened is neutrons try to penetrate through the fuel because of the high absorption cross-section for the fuel at the resonance location. The neutrons will be absorbed not far from the surface of the fuel. So the fuel itself will work as a self-shield to itself, self-shield. So you will self-shield the interior of the fuel from the neutrons, because the neutrons will not be able to penetrate deep until the center. Yes, there is a fraction of the fast neutrons will penetrate into the center, but not all the neutrons will be able to penetrate. Not all the neutrons that's subject to the hitting the surface of the fuel will be able to penetrate. So this is a phenomena that we call self-shielding. So if you look at the flux in nuclear reactor, you'll notice that the flux in the moderator is like this. Once you come closer to the fuel, you'll notice that there is a drop in the flux. Then the flux will be something like this. Goes to infinity, means maybe there is no flux at all, or maybe there is a small amount of neutron flux inside the fuel. So this is a phenomena called self-shielding. So what's the importance of this self-shielding phenomena is the resonance escape probability will increase in self-shielding. Why? Because you reduce the absorption inside the fuel, because not all the neutrons will penetrate in. So usually resonance absorption took place in fuel or moderator. In fuel, because the moderator does not have resonance. So you reduce the number of neutrons penetrating inside, so you reduce the total number of neutrons that will be absorbed inside the fuel at high energy. So in this case, the resonance escape probability will increase. But the F will decrease. Why? What's F? Thermal utilization. So why it will decrease? because also you reduce the total number of neutrons absorbed in the fuel because of self-shielding. But the increase in P will be more dominant than the decrease in F. So in this case, you will notice that you will have increased the multiplication factor, because the multiplication factor is just eta epsilon FB. So if B increases and F decreases, so that the total effect will be an increase in K infinity. And this, once you do the fuel lumping, you can reach to a value for K infinity equal to 1. So this is usually what they did in the first nuclear reactor when they designed the first nuclear reactor using graphite, the graphite moderated reactor in the Chicago site. So let's talk about time-dependent chain assembly. Time-dependent chain assembly. And let's define the average time L, average time required for a fission neutron to slow down and get absorbed in the or leak out. So this is average time for neutron, for fission neutron to get absorbed or leak out from the system. So this is the time it takes the neutron from the moment it is generated or being born as a fast neutron in fission until it gets either absorbed at the end or it gets leaked from the system. So this is like a lifetime for the neutron. How long from birth to death? Death might be from eaten by shark inside the reactor, which is the absorbers, or get expelled from the cell, and it will also die if it gets out of the water, like if we are talking about fish, for example. So it's the same analogy. So now this time is given by 1 over nu sigma fission multiplied by the velocity. Some of the books will write the lifetime, this lifetime, as in Stacy, he wrote it as 1 over nu sigma fission V, where V is the velocity, nu is the number of neutrons produced per fission, and sigma fission is the fission cross section. Some other books they will write this as sigma absorption V. What's 1 over sigma absorption? When we deduce a factor a couple of lectures ago, and we said that it's equal to 1 over sigma absorption. Do you remember what's this factor? Yes, exactly. So 1 over sigma absorption is mean free path and velocity. So if the neutron was born here in fast fission, go make a collision, then another collision, then another collision, then another collision, then get absorbed here. So absorbed here and born here. So this is the mean free path, lambda. And if it moves with a velocity v, so if you divide lambda over v, distance over velocity, what this will give you? Time. So this is the lifetime of the neutron. Did you understand? So this is lambda over v, and this is time, unit of time. So this is why they call it like this. So he wrote the lifetime as this. So if we started with initial number in the reactor core, and this is the neutron population. So neutron population at time t equal to 0, t naught. So after one lifetime, after 1 L, one lifetime, what do you expect N to be? This is a multiplying system, a reactor multiplying system. After 1L, one lifetime. So neutrons are right now we have N naught neutrons in the reactor. KL naught. Did you understand why? Because K, the multiplication factor, is the total number of neutrons at certain generation divided by the number at the previous generation. And the two generations are separated by the neutron lifetime, the average neutron lifetime. Because this is the average neutron lifetime. The average time, yes, because lambda is the average distance, which is the mean free path. Yes, so this is KL. So after after second 2 cycles, 2L, this will be what? K multiplied by KL. Yes, because the previous generation was KL. I have to multiply it by K. So this will give me what? K square L. After M cycles in the reactor, M cycles or lifetimes, this will give me K to the power of M multiplied by L. Sorry, not L. This multiplied by N naught. Multiplied by N naught. Multiplied by N naught. K multiplied by N naught. I'm sorry for the mistake. So Km multiplied by N naught, the initial number. Now, usually, and keep this in mind, usually in thermal reactors and fast reactors, in thermal reactor, L in the order of 10 to the power of minus 4 seconds, 0.1 millisecond. What does it mean? It means that the neutron will take 0.1 millisecond from the moment, on the average, from the moment it is born in fission to the moment it will be absorbed. On the average, in thermal reactors, 0.1 millisecond, very fast. Okay, so what about fast reactors? What do you expect? You expected shorter or longer?
Shorter.
Why shorter?
It's fast. It's all fast.
Fast neutrons.
Takes long.
Yes, and in fast reactors we do not allow the neutrons to thermalize and become thermal. Just they will induce the fission at 100 kiloelectron volt, which is 10 to the power of 5 times order of magnitude. So you expect this to be what? To be 10 to the power of minus 6 to 10 to the power of minus 9 second, minus 8 second. So 4 order of magnitudes for thermal reactors, for fast reactors. So just remember those two figures of merit because they are very important in controlling a nuclear reactor, and this is what we will see maybe before the end of this lecture. But remember those two figures of merit: 10 to the power of minus 4, 10 to the power of minus 8. 4 order of magnitude, 10 to the power of minus 6 to 8. Now let's assume that there is a change in the cross section, absorption cross section, delta. Let's say delta sigma. I change sigma whether I will increase it or I will decrease it by 0.5%. So 0.5% is what? 0.005. Okay, so the change in delta sigma, the absorption will be equivalent to delta K of 0.005. Yes? You change the multiplication factor by 0.005, because what controls the multiplication factor is the absorption. Yes? So you increase the absorption or decrease the absorption. Let's say you increase it by 0.005. So what will happen as a result of this delta K change? So let's assume that N as a function of time equal to N naught multiplied by K to the power of M. And this is this formula here. This is N after ML time, ML, where time equal to M multiplied by L, yes? This M here is how many cycles, how many lifetimes. So let's assume that T equal to ML. And let's assume that this time, just 1.1 second. Just 100 milliseconds. 100 milliseconds is how many L's? L is what? 10 to the power of -4 seconds in fast reactors. Yes? ML is equal to 0.1 second. So M is equal to what? 10 to the power of -4 divided by 0.1. So this would be what? 10 to the power of -3. 10 to the power of -3, or sorry, 0.1 over 10 to the power of -3. It's the other way around. 0.1 divided by 10 to the power of -4. 1,000. So how many cycles 0.1 second is? 1,000 cycles. So we changed the multiplication factor by just 0.5%. So it will be, instead of 1, which is critical, it will be 1.005. And I want to look for what's the neutron population after 1,000 neutron lifetimes. 0.1 second. 100 millisecond is 1,000 neutron life cycles. How the neutron population will look like in the nuclear reactor. So all what we want to do is to apply the formula that we just show here. And the formula states that N as a function of L, ML, T equal to ML equal to what? 0.1 second is just equal to the starting N multiplied by K to the power of what? M. So this will be N naught to the power of 1.005. This is the new K. And instead of 1, it became 1.005 to the power of 1,000. This will give me 150 N naught. What does it mean? Mean that if you start with initial number of neutrons, N naught, and you just change the cross-section positively, you add more neutrons, let's say more, change the cross-section, let's say you add more fission to the reactor, and based on the lifetime for the thermal reactor, which is 0.1 millisecond, in 1,000 neutron lifetimes, you will multiply the initial number of neutrons by 150 in just like blink an eye. You make something like this, and you will increase by 150. Later on in the course, we will discover that number of neutrons inside the core corresponds to the power. because the number of fissions is the number multiplied by energy per fission will give you power. Number of fission per second multiplied by energy per second, joule per second is watt, so this is power. So if you have 1 megawatt, you will end up after a blink of an eye of 150 megawatt. So it's very, very high, very huge, just based on the 0.1 millisecond lifetime. So if on the other side the change is not positive, the change is negative, so I will have n of t equal to ml equal to 0.1 second, and in this case n is still n naught, but the multiplication factor, instead of 1.005 it will be 0.995 to the power of 1000. This will go to 0.0066 n naught. So again, I will drop the neutron population a lot. It will be even less than even 7%, less than 7% of its initial value after a blink of an eye. But this is based on what? Based on the neutron, what we call prompt neutrons. So what's the story here? The story is, in nuclear reactors, there is two types of neutrons produced. One is prompt. The other one is delayed. Okay. Prompt neutrons are neutrons that's generated directly from the fission. So the compound nucleus is formed. You split the nucleus to 2 halves, or whatever the ratio, according to the fission yield. And then you produce 3 more neutrons. Those 3 more neutrons are produced simultaneously. So this is called prompt neutrons. It took something like 10 to the power of minus 14 seconds to get generated or so. So those are prompt. So the cycle will be very, very fast. The time they are generated, it takes nothing, 10 to the power of minus 14. Then they will spend some time hanging around in the sea until they will be eaten by the big fish, sharks, or they will leak out from the sea to the shore. In the 2 cases, they will be lost. So this lifetime is just 10th of a millisecond. The other type of neutrons, they are called delayed neutrons. Where they come from? The fission products that's produced as a result of fission. Some of those fission products will be radioactive. Then they will go in nuclear decay processes. And some of those, they end up with, let's say, beta decay, then they will emit a neutron. They will have excess binding, not binding energy, excess activity, reactivity, natural radioactive activity. Then they will, or excess energy inside, then they will emit neutron. Those radioactive nuclei, they are called delayed neutron precursors. Delayed neutron precursors. So they are precursors for the delayed neutrons. So if you look at those neutrons, example for this one is just the uranium-235 plus the neutron will give you the barium plus the krypton plus, on the average, let's say 2.45, but let's say those are 3 neutrons. Those are the fission. But here we will notice that in chapter 2, if you look at the table, I think chapter 2 or maybe later chapters, you will notice that we have six groups of radioactive nuclei. What do we mean by group? Each group will have, let's say, 7, 10, 8 number of nuclei. They classified the number of the nuclei according to the decay time. So they said, okay, those group of nuclei, they have similar decay time. So let's say 0.1 millisecond. Those number of nuclei, they have similar decay time. So they classify those nuclei. I think, I don't remember the total number, but let's say 6 multiplied by each one of those group, maybe 5 or 6 or 7 isotopes. Maybe you will have 50 isotopes in total or so, the delayed neutron precursors. So for those 6, if you look at them, you will notice that you have decay time from a fraction of a second up to 57 seconds. So the longest decay time for the group is a minute. So it will take a minute for the neutrons to come out as a result of the radioactive decay from those delayed neutron precursors. A minute, a whole minute. So there are 6 groups, and those groups are characterized by lambdas, lambda 1, lambda 2, up to lambda 6, which is the decay constant. The inverse of the decay constant, of course, is what? The average lifetime, and 0.693, which is ln 2 over lambda, will give you half-life. You remember this from the last year in ES 495. So scientists will look at this and say, okay, let's calculate how many neutrons will come out from the fission. And then, as I told you last time, we have, on the average from the fission, we have nu. Yes? Among those nu, 2.45. Let's say I will count thousands of those fissions, 2,000, a million. I will look for million neutrons, and I will say, from those million neutrons, there is, let's assume, there is 900,000 and 900, let's say 978,000. They are prompt neutrons, the rest are delayed. Okay? Then they will look and they will say, okay, I will get some person like me, then I will shrink myself until I become like the neutron. And I will have a net, and I will look for the neutrons with a magnifying glass and the net, but this net is a little bit fancy net that will tell me what's the energy. Then those neutrons coming from the fission, the average energy is around 1.98 MeV. They come from the sky distribution and so on. The neutrons that come from the delayed neutrons, the average energy is around 0.7 MeV. Then I will say, okay, let me look for what's coming from each of those 6 groups. Okay? And I will give the group number 1 a fraction. How many neutrons come from this group? Group number 2, a fraction. Group number 3, a fraction, and so on. So this fraction is beta 1, beta 2, up to beta 6. So beta is just the delayed neutron fraction in the group. And if you want to get the total number of delayed neutrons, all what you will do is just add them all together to get the total delayed neutron fraction that will come from all groups. So beta is just the summation of beta I, and this is from I equal to 1 to 6, and this is the delayed neutron fraction. Usually for uranium-235 is around 0.0065. So 6.5% of the neutrons getting out from the fission, 6.5% of the neutrons getting out from the fission are coming from delayed neutron precursors. And 93% 3.5% are coming as prompt neutrons. So it's a very, very minimal, very small, very trivial fraction, but has very pronounced and important effect on the kinetics of the nuclear reactor, as we will see here in a minute. So, did you understand what's going on right now? Yeah. Yes.
The fraction from the delayed or from the whole number of neutrons?
No. The whole number of neutrons should be 1. Should be nu.
So
There should be 1, the
from
fraction.
The delay itself.
Huh?
A fraction from the delay.
No. This is if you will bring how many neutrons. Let's say you assume that you count all the neutrons coming from the fission. Let's say 1 million.
Okay.
6.5% of the million will show up as delayed. They will show up after. They will not come promptly from the fission. 93.5% of the neutrons will come out as prompt. 6.5 will show up later. Later means from point to a fraction of a second up to 57 seconds or a minute. And it depends on the fuel that you are using. If you are using uranium-235, this is what? 0.0065. If you are using plutonium for fast reactors, plutonium I think 239, this is 0.0022, which is even smaller. And we'll notice that this will show a pronounced effect on the reactor itself. Okay, guys, I will show you why it is very important, those numbers. Just bear with me. So this is, let's now go back again and do the same analysis that we just did here for this time behavior. This is just a back of the envelope calculation for the time behavior on nuclear reactors. So let's assume that this is the formula that will govern the time rate of change of the neutron population. dN by dt is just k minus 1 over L multiplied by n of t plus source of t, where this is external source. And this is just the neutron population at time t, not neutron population at time t, and k is the multiplication factor, L is the lifetime, and again this is just the normal formula here. Let's assume that k is greater than 1, which is supercritical reactor. And let's assume that you make the reactor supercritical until you reach to a situation where dN by dt is 0. There is no change, let's assume. So this will give you k minus 1 over L multiplied by n of t plus s of t equal to 0. So if you rearrange, you will get n of t is just equal to negative s of t multiplied by L divided by k minus 1. So the source that you put in the reactor is always positive quantity. Yes? The lifetime is always positive quantity. If the multiplication factor is greater than 1, so this is always a positive quantity. So in this case, n of t will be negative. Yes, this is positive, positive. This difference is positive. N of t will be negative. This means that there is no solution for this equation. It's wrong. N of t cannot be negative quantity. The neutron population cannot be negative quantity. So the equation does not have a solution for k greater than 1 and steady state. So if your k is greater than 1 and you assume that it is a steady state, the equation does not have solution. Because dn by dt equal to 0, this is what? Steady state. Yes? If you assume that k is greater than 1 and also it is a steady state, it will give you nonsense solution. And this makes sense. K greater than 1, you are supercritical, and you expect that your neutron population will do what? Will increase with time, will not stay constant. So this does not make sense. So when you have a k greater than 1, you expect to have a growing population of neutrons inside the core. Let's assume instead that you make k equal to 1 now and look for what will happen for the neutron population. So k equal to 1, and now you assume, let's say you assume also steady state, so 0, k minus 1 over L multiplied by n of t plus s of t. So this will give you what? N of t will be just s of t multiplied by L. This is, let's say, very, very near to 1. Again, there is no unique solution for this case. Then let's say if k is less than 1, we assume that k is less than 1. So in this case, and also I assume steady state, so this will be, I can replace k minus 1 by minus 1 minus k divided by L n of t plus s of t, and in this case I will reach to n of t equal to s of t L 1 minus k, and this is called asymptotic solution. What do we mean by all of this? We mean the following. If you have a nuclear reactor without external source, a nuclear reactor without external source, so this is n of t. Here, no source, and this is the time. If I have k equal to 1, what do you expect the neutron population will be?
Straight line.
Straight line. Okay? If k is greater than 1, so I expect something like this. Yes? If k is less than 1, make sense? Makes sense. Now, if I have a source, this is the time again, this is n of t, and I have a source with source. If k with the source, if k is less than 1, what will happen? If you have a source, external source in the reactor, and k is less than 1, what will happen? If there is no source at all, k less than 1, you have neutrons, it will be absorbed, decrease, 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 decrease until you reach to what? 0. But because you have external source, it keeps spitting neutrons into the core continuously. You get absorbed the neutrons, but it spits a lot. Yes? So you will reach to a steady state value. So k less than 1 with extraneous source, you will achieve a steady state. K less than 1, K less than 1 with source. If K is equal to 1, I just showed to you that the case where K is equal to 1, N of T will be what? Source term multiplied by L. L is time. So this will be what? Straight line. So you are increasing with time. K is equal to 1 with source. So when you have a situation, a critical situation, and you put inside your trigger reactor a source, although you are critical from the point of view K equal to 1, but you are increasing the number of neutrons. Why? Because you are feeding those number of neutrons by a constant. So you will increase based on this constant linearly. If K is greater than 1, you will have something like this. K is greater than 1. So if in the exam I asked you plot the two situations, maybe it's one of the question in the exam, and I ask you what's the difference between a reactor with a source and a reactor without a source. Just show me what's the difference. So here our reactor, for example, the trigger reactor, when we try to run at a very low power, if you take the NE648, the nuclear reactor experiment, you will notice that sometimes we run at near 0 power, 1 watt. Okay? And sometimes the reactor is not critical, it's subcritical, but you have a 1 watt of power continuous. And usually the extraneous source will help keep the reactor what? Critical. So you are critical based on the extraneous source. Do you understand? Yes.
So you would only use this extraneous source for like startups to overcome poison and stuff?
Yes. Usually the extraneous source in the nuclear reactor, you do not have enough population to make the reactor will sustain itself. So you put the extraneous source until the reactor will sustain itself, then you remove it out at high power. Of course, at high power, the neutron population is very high compared to the extraneous source, so it does not make any sense if you want to remove it or not. But usually the extraneous source is to make the startup of the reactor every time, especially if you do not have photoneutron emission inside your reactor core. Like, again, I just stated in the first lecture, I think, that our nuclear reactor, when I used to work in Egypt, it has a beryllium reflector, and beryllium will absorb gamma rays and emit neutrons, and in this case you do not need the neutron source to be present after the first run. So this is what we meant here. Okay, so now let's just do some more analysis to show you how the delayed neutrons will change completely the performance of the nuclear reactor. So let's assume that C is the concentration of delayed neutrons precursors. Delayed neutron precursors. And lambda is just the decay constant. So when you write the equation for the continuity for the delayed neutrons, how the delayed neutrons are produced? If I said, what's dC by dt? Let's assume that we have only one group for right now, not 6 groups. And this one group has a concentration C, like number of neutrons per centimeter cube. So this is dC by dt. How dC will it change by dt? If you are studying any phenomena and you want to study rate equation, so you will say time rate of change equal to production minus losses. How they are produced? They are produced from the fission. So what's the total number of fission? sigma fission phi. Yes? Sigma fission phi is total number of fission per second per centimeter cube. This is per centimeter cube. But this is not the total number of delayed neutrons or anything. If you multiply this by nu, this is what? Total number of what? Of neutrons produced in the, per fission, per centimeter cube per second. But beta of those neutrons are what? Are delayed neutrons. If we assume that every delayed neutron is coming from one delayed neutron precursor, so this is the rate of production of delayed neutron precursors. Yes? If we said we are looking for the time rate of change of moms, pregnant moms in the city of Manhattan, then what you will say, I don't know what's the total number of pregnant moms, but I will look for total number of children, fast children. I want to classify the fast moms and fast children and so on. So I say, okay, I will look for the fast children. I will say this is the total number of fissions, pregnancy. Each pregnancy will give 2 child on the average. There is no 2.5 child, of course. So 2 child. Then this is the total number of children. Among those children, there is children that are very, very fat, with belly, like me. And there's children that are very skinny and very fast. So the fraction of those children is 10%. So if you multiply this, you will say, okay, if every mom gives a birth for only 1 child instead, for those delayed neutrons, so I have so and so moms. Then the losses in case of is miscarriage. So it will be lambda c, decay. Yes? So this is the first equation. I will stop here because we already ran out of time. Then next time I will continue.